Hey everyone, and welcome to this explainer. Over the next few minutes, we're going to completely demystify the science behind one of nature's absolute most beautiful sights. We're going to break down the physics, we'll challenge a little bit of history, and I promise you, we are going to fundamentally change the way you look at the sky.
So, let me ask you a question right out of the gate. Can you actually touch a rainbow? I think we've all probably reached out toward one at some point, right? Or maybe you tried to find its end when you were a kid, looking for that elusive pot of gold. But today, we're going to deconstruct this colorful myth using pure physics, just to understand exactly why this gorgeous arch isn't a physical object you can hold at all.
Okay, let's dive right into this. Section 1, the journey of sunlight.
To really wrap our heads around this illusion, we first have to track a single invisible beam of white sunlight traveling millions of miles from the sun right down into a tiny floating raindrop in our atmosphere. It's basically a three-step process. First, the light enters the raindrop and it bends. Second, it reflects right off the back inner wall of that droplet. And third, the light exits, bends a second time, and spreads out. It's absolutely wild to think about, but that tiny droplet of water is basically acting like a microscopic factory. It's capturing plain white light and transforming it into a spectacular visible spectrum.
Now, the very first essential word you need to know to understand this whole process is refraction. This is simply the bending of light as it passes from the thin air into the much denser water. And when it hits that water, it actually causes the light to slow down.
But, refraction doesn't work alone. It's got a partner in crime, which brings us to dispersion. Dispersion is the separation of that light into different colors, and this happens because each individual color bends by a slightly different amount. Red light, for instance, has the longest wavelength, so it kind of resists the bend. It bends the least. Violet light, on the other hand, has the shortest wavelength, so it bends the most. That exact tiny difference in bending is what spreads the light out into that wide, beautiful arch of color we all instantly recognize.
Which brings us to Section 2, the magic number 7.
Think back to grade school for a second. Why are we all taught that rainbows have exactly 7 colors? You know the drill: red, orange, yellow, green, blue, indigo, violet. If light is a purely physical phenomenon, why on earth is it divided so perfectly into 7 categories? Well, back in the 1600s, the brilliant English scientist Isaac Newton was studying light using a glass prism. But when it came to categorizing the actual colors he saw, he essentially forced the number 7 onto the rainbow. And here's the crazy part. He chose this specific number not purely out of scientific observation, but partly because of his own personal beliefs about its mathematical, mystical, and cultural significance.
So the crucial takeaway here is that Newton's rigid 7 colors, they aren't actually the whole scientific truth. The spectrum actually contains a continuous, unbroken range of wavelengths. Rather than neat little separate bands of color like a coloring book, sunlight blends countless shades smoothly into one another. It is literally an infinite, seamless gradient of light.
Now, what's really interesting about this next part is how you actually experience it. Let's move into our final segment. Section 3, your very own rainbow. Let's shift our focus from the physics high up in the sky down to how you, the observer, physically interact with this optical illusion right from the ground. Think about the difference between a standard primary rainbow and a double rainbow. Have you ever been lucky enough to spot one? A primary rainbow happens with just one reflection inside the water drop, leaving the red color on the outside arc. But a double rainbow? That requires the light to bounce and reflect twice inside the raindrop. Because of that second bounce, the light actually loses some of its energy. This means the second rainbow appears fainter, it sits way outside the first arc, and the order of the colors is completely reversed.
And hey, you definitely don't need a massive rainstorm to see this physics in action. You can find rainbows in waterfalls, everyday fountains, garden sprinklers, sea spray, and even just mist. As long as the sun is shining directly behind you and there are water droplets suspended in the air in front of you, you can find a rainbow pretty much anywhere.
Okay, prepare to have your mind bent just a little bit here. Literally no two people see exactly the same rainbow. No way, right? But it's true. Because a rainbow depends entirely on your exact position as the observer and the specific angle of the light reaching your eyes. The rainbow you see is bouncing off a completely different set of water droplets than the person standing right next to you. The specific light reaching your eyes makes your rainbow entirely unique to you.
Which brings us to our final, kind of profound question to leave you with today. We now know for sure that rainbows are untouchable optical phenomena. But if no two people see the exact same rainbow, what other beauties in nature are entirely your own?
I want you to think about that profound thought the very next time you see those brilliant colors stretched across the sky. Thank you so much for joining me for this explainer, and keep looking